All right, howdy y'all. So in this video, we're going to be doing 8.14. So one thing that we need to cover prior to being able to state the theorem, we need to define a function real quick. So we're going to define the function given a function phi on Rn with t greater than 0, phi sub t of x is going to be defined to be the determinant of t inverse times the identity matrix, and by an identity matrix times phi of t inverse x. So where does this guy come from? So there's a theorem in chapter 2, it's 2.44, it says that if I have a Lebesgue measurable function in R, and t is an element of G ln R, then f composed t is also Lebesgue measurable. And if f is in L1, then we get the identity, we get the statement that the integral of f of x dx is equal to the determinant of the element of G ln R times f compose that element dx. And again, these guys live in Rn. So clearly, the identity, a scalar multiple of the identity matrix lives in G ln R. And because x lives in Rn, we can think of T inverse, instead of being a scalar multiple, we can think of it as being an element of G ln R because it's just this same identity matrix. So this is in fact meeting with this statement here. So we're going to use this to our advantage. So what we then get, based on this definition, is a simplified version of this inequality. That equality, we get that the integral of phi sub t is just equal to the integral. And this is, again, because this guy lives in G ln R. And this is theorem 2.44. So we're going to need that identity in a second. Now that we have that definition, we're going to suppose that phi is in L1 and that the integral of phi across Rn is A. So there's three parts to the theorem. In this video, we're going to be doing A. In the next video, we'll be doing B, and then third video C. So we're going to break it up into three different parts. So we have A, if f is an LP with p between 1 and infinity, not including infinity, then the convolution f and phi t goes to AF in the LP norm as t goes down to 0. So, sorry, cat. So, to start the proof, we're going to take the convolution and subtract off AF, and then with respect to the P norm, show that this thing is in fact going to is going to 0. So we expand our convolution, and then we write this guy here as this statement there. And again, we know that the integral of phi of x is equal to A, and from before we get that's the same thing as the integral of phi sub t. So what we're going to have is that times f of x, but both of these are with respect to the x variable, whereas this integration is with respect to y. So we can pass that through, and we end up with fx minus y minus f of x times this f sub t of y dy. Okay, now what we're going to do is we're going to set y equal to tz. Then again, we would get that. Then we would get that z is equal to y over t. So when we substitute our y here, we get z and we can drop the subscript of t because of the way that we define phi sub t having t inverse inside. And then secondly, we substitute the y here to get tz. Now we have this guy here, which is just a translation of f by tz. So we can pull out, we can write this as a composition where I am composing with the translation tz on f of x, and then subtracting off f of x. Now, what we have at this point is we need a second identity. It comes from chapter 6.3. So it was not one that we covered in class, but it's called Minkowski's inequality for integrals. So what we have is that given the necessary conditions, this is going to be the So we end up with this inequality. So this guy here is less than or equal to the integral f, sorry, this is with respect to the p norm. And here, with respect to the p norm. So what this is basically saying is that we can pass the p norm through given the necessary conditions. And it turns out that at this point, we've met those conditions. So by Minkowski's inequality, we get that if I take the p norm of, sorry, let me actually, give me 1 second. So if I take the p norm here and on our last step, what we get is that the p norm here is going to be less than this integral. But again, the p norm is with respect to x. So this guy is just going to get an absolute value slapped on him. So we end up with phi sub z. And then what we notice here is that this guy here, this one here, is in fact less than 2fp. And this comes from the fact that this is a norm, so we have sublinearity, so we can split this, and that would be norm tz of f plus the norm of fp. And then because translations are invariant, or sorry, are continuous with respect to p norms, we can drop them all together. So we just get that this is simply less than 2fp. So we get that it's bounded. Secondly, by proposition 8.5, because this guy is continuous with respect to p, we get that this is in fact going to 0 as t goes to 0 with respect to the p norm. So what we have now is that this guy here, the thing that we were trying to show, so f convolution phi sub t minus af is bounded, and is bounded by a LP function, and then we can use the dominating convergence theorem to get that since t is going to 0 here, we get that this guy is going to AF with respect to the p norm as desired. So dominating convergence theorem, so we have bounding, we have that it's going with respect to t, and then we can apply the dominating convergence theorem. Okay, so that's going to be A. B is very similar. We're just going to have to go over a few of the details and swap out a few of the norms, because with B, we're going to be looking at it for bounded uniform continuity. Or we're going to have F be bounded and uniformly continuous instead of being an element of LP. So I will see you guys in the next video.